What's up, all you badass mathematicians? So today we're going to introduce the idea of derivatives. And so to do that, we're going to first take a look at this function, our f of x equals x squared. And let's think about it in a specific context. So we'll let f of x be the distance traveled, x hours into a road trip. And so here we have our function graphed, and on the y-axis is our outputs, which is the distance traveled, and on our x-axis is our inputs, which is the time. So the first thing that we're going to ask is, what's the average velocity between x equals 1 and x equals 4? So my thought process here is that I know that I'm going to end up wanting something of the form miles per hour. So I want to figure out how fast I was going on average, the duration between hour 1 and hour 4 of my trip. Then we can figure out how far we've traveled between those times. And then to average out over all those hours, we would divide by the total time that's elapsed, which is 4 minus 1. So then this is equal to 4 squared is 16, minus 1 squared, all over 3. So this would give us 15 over 3 miles per hour. So notice what's interesting here, what we've just done, is we're taking our change in our y values, change in our outputs, and dividing it by the change in our inputs. So this should be familiar for our linear functions as a way to calculate the slope of our line. So then maybe the next question is, what line is this the slope of? And let's change colors. So here is 1 f of 1 and 4 f of 4. This line right here is called a secant line. So the slope of this secant line here is going to be our average rate of change between x equals 1 and x equals 4. Next, what we're going to want to look at is we want to estimate the velocity at x equals 1. And so what we want to look at is, while we're driving, when we reach x equals 1, what is our speedometer read? So we're trying to figure out instantaneously at x equals 1, how fast were we traveling in our car? So now one interesting thing to note is that one possible estimate could be this average velocity between x equals 1 and x equals 4. We should then follow up with, is it a good estimate? Let's try and think of examples of maybe where it would be a good estimate and where it would be a bad estimate. So for example, maybe if I was traveling the same speed the entire time, then if I average out over the interval, then I should get the same speed no matter where I was in that interval. So that would be an example of where it would actually be a good estimate. But what if instead at x equals 1, my car was parked for 30 minutes and before I finally decided to keep driving between x equals 1.5 and x equals 4? Then our average rate of change is actually going to be completely off, because our true speed would have been 0 at x equals 1. So maybe we could figure out an average velocity over a more helpful interval. So let's say we were at rest between x equals 1 and x equals 1.5. Then maybe we can take the average speed in that interval to give us a better estimate. So let's try smaller interval. So to recap, we're saying that our interval in part A is just way too wide. If we were at rest for the first 30 minutes, then this would completely miss that and mislead us in estimating our actual velocity at x equals 1. So let's try x equals 1 and x equals 1.5. So then the average speed then would be f of 1.5 minus f of 1 all over 0.5, which is our change in x values. So then this would be equal to 1.5 squared should be like 2.25 minus 1 all over 0.5. So this will equal, so 1.25 is the same as 5 over 4 all divided by 1/2. So multiply by the reciprocal, and that's equal to 10 over 4. Okay, so it should be a shallower slope like that. So now our line is actually going to be a little shallower, giving us a better idea of what our speed is at x equals 1. But the issue is that this is still way too wide of an interval. So now imagine the first 15 minutes we were standing completely still. So our estimate for what we were doing when we were standing still would be that we were traveling 2.5 miles per hour. So then try smaller interval. So maybe x equals 1 and x equals 1.1. But notice that no matter how far we go, I can always complain that the distance between these two numbers is too large to give us an accurate enough estimate. However, our estimates will be getting better and better. So we can expect this. 1.001 to be better than our estimate from taking the average velocity between x equals 1 and x equals 1.1, which is then better than this, which is then better than our really wide interval. So this is now where our the tool we learned with limits becomes super helpful in helping us define our derivative. So this is how we define the derivative. So the derivative of f of x is defined by the limit as h approaches 0 of f of x plus h minus f of x all over h. So let's really think about what we're describing here. We're looking at some x value. So let's think of x equals 1. And then we're talking about x plus h, which is another x value. So we can think of this as x, and then we can think of this point as x plus h. So we're saying, give me 2 points that are really nearby each other. So what we're really doing is we're taking our average and we're trying to get a smaller and smaller interval to get a better idea of what the instantaneous rate is at x. So when we're talking about the limit as h approaches 0, we want to shrink this interval as small as possible and keep averaging over a smaller and smaller interval to get a better idea of what's happening at our point x. So then what our derivative actually is graphically. Ooh, I freehanded that line. That's nice. It's actually going to be the slope of this tangent line. Derivative is slope of tangent line. So this line is tangent, meaning it touches our original curve at exactly 1 point. And what's so powerful about the limit is that when we're shrinking this interval so far close to 0 that we're getting a better and better approximation of this line. So to recap what we went over today is we explored this idea of an average rate of change. And now we're using that idea to estimate what our speedometer is actually going to be saying at x equals 1. So we want to figure out our instantaneous velocity. What does our speedometer read at x equals 1? And the way that we're achieving this is by using our tool, which is the derivative. And what the derivative is essentially saying is keep shrinking your time intervals. So instead of looking at x equals 1 and x equals 4, look at x equals 1 and x equals 1.5. But wait, that's too large of a time interval. So keep looking x equals 1 and x equals 1.1. Still too large. So keep shrinking until the time interval is so small that it actually will approximate the slope of this tangent line. And it will tell us what our speedometer is going to read. It will give us a good enough estimate. And in the limit, it will give us a perfect reading of what our speedometer should read, what our instantaneous velocity is. Yeah, so that's all I have for today. Please leave any questions or feedback in the comments. Thank you for listening.